Okay, welcome to MCO455 Lab 1. What we're going to do today is we're going to quickly review questions 1, 2, and 5 that we did the other day in theory class. We're going to cover questions 3 and 4, the adding, subtracting hex binary with NZBC, and then we're going to do the rest of Lab 1. So you need to have these materials purchased as soon as possible, and you need to have at least the Freedom K64 by the end of next week or the start of the following week. The other thing that you need to do is also have registered your microcontroller board if you want to get credit for Lab 2, 3, and so on in any lab quizzes after that we do. So it's important that you get that registered so we make sure that you have the parts in place. This week we're working on Lab 1, and next week you're going to be doing Lab Quiz 1. In Lab Quiz 1, you'll be given both periods if you need it, but chances are once we go through the stuff today, you should have most of it ready to go and be done maybe in 15-20 minutes. So before you come into your class next week, you have to have everything finished in Lab 1 before you come in. Once you've got that done, you're going to prepare for Lab 2 by creating an embed account, and then the following week, you're going to have a chapter quiz worth 2%, as well as a lab quiz based on the stuff that you're going to do in Lab 2. It's got a thing where it says, here's a video. That's anything in pink is a video, and this is a link to where you go to actually create the embed account. So here's how you do it. There's where you go. Here's how to do it. That's where you get it. So all this stuff is pretty straightforward. Now what you're going to see here is something very akin to what you were doing in the last couple of semesters for PRG 1 and 2, console applications. You'll notice integer main void, very similar to what you've done, input equals get C standard in. So these are pretty basic things, except you've got now something called number sign include embed.h. We can see something that's going to involve different types of programming. So while loop, which you guys really, I couldn't believe how many people when I did PRG 2 said, oh, I do everything with a for loop. You can't. So things like that, and also things such as where you've got function prototypes, function definitions, function calls. You guys have a little bit of problem with that. And actually, if you can get this one working before the end of this week, you'll be able to, put in numbers, and it'll say, I'm going to do the and or an exclusive or to check that chart on the last part of lab number 1. So the addendum basically is showing you week by week where the marks are, and the first evaluation is here. Now, lab 1, if we take a look at it, again, all the stuff here that's bold, you do not circle. You're just going to circle anything over here that's not correct. So we saw the other day that this isn't correct, so that's one of the things that you're going to circle. Here, the octal, anything in bold you do not circle, but any conversions in binary and hex that are wrong based on this, you circle. Again, here this hex is perfect, so you're not going to circle any hex, you're going to circle any binary or octal that is not correct. The ASCII chart on page 26, so you find this is capital Y, small letter O, small letter U, a space, and so on. We'll talk about that again. Now, we're going to sort of pick up here when we continue on, but you should already have 1, 2 done. And question 5, again, it's bold is correct. So this is correct. Circle any of these things that aren't. A9 is correct. So circle any of these things that are not equivalent to that. And as we go through, we're going to learn about all these other things in here. There's 3 different programs here, one in binary, one in octal, one in hex. And let's take a look where that comes from. Back in the 60s, this was a 1960s home computer. And this was it in machine code. So you had a series of 1s and 0s that you plunk into these switches here, hit the deposit, and that instruction went into memory. Because digital computers, whether you're doing DGS or whatever, only understand patterns of voltages. It doesn't matter whether you got the most expensive M1, Apple new computer, any computer that you got, PCs, whatever, anything from a microcontroller to a mainframe, this is the only thing the computer can really understand is patterns of voltages. Now, in the old days, a 1 would typically mean 5 volts and a 0 ground, but now it's, for our microcontrollers, it's 3.3 in ground. And for newer stuff, even it's 2.8 in ground, because one of the things you're going to find for portable devices, the higher the voltage, the more heat there is, and you want to dissipate heat and not have heat. So that's why the voltages for these binary patterns are going down. So in the 60s, we actually had to work at the level of the machine, and that's why the binary that's here is called machine code, because you're working right at the level of the machine. The next level up was saying, okay, well, let's group these switches in groups of 3, and then we could actually code an octal. And it was really, the 6 here meant flipping 3 switches, this was another 3 switches, and so on. By the 80s, this is where we started getting into a little bit better things, where you'd hit an A and you get 1010, hit a 5, you get 0101. So it's a lot better and the technology improved. But one of the first things you're going to see is that all of these numbers that are here made absolutely no sense. This is the only thing that made sense to the computer, or any computer really. This was just a more compressed and a more compressed form. This is the first level of programming that made any sense to us, like load a hex number for A, add to that a number to C, store that in address 80 here, and sit in an endless loop. This is the first thing that made any sense to humans. And then what you did then was we got to a higher level, because here's the assembly language you just saw on the previous page. Here's what it is in C. Now notice this says void main void. And the difference between that and what we're used to, which is integer main void, is we have an operating system that we return to once our code has been executed. And so when we say integer main void, then we return a 0 to our operating system to say, yeah, our program is terminated properly. Otherwise, Windows will crash for no apparent reason. But anyway, so for this one, it's void main void, because in the old days, all of the stuff between the brace brackets was your operating system. So old cell phones, the old flip phones from back in the day, those all used void main void, because you would program right in here, and any code that you had in here with those menu-driven systems, that was your whole operating system. There was no operating system for it to go back to. Your code was the operating system. The hex codes here in yellow are the ones that you're going to use for question 2. Let's take a look at our theory portion here. So this is getting back to our AC here, and some of the stuff in here is going to be very helpful for you, because if you go through video lectures here, Lab 1 Part 1, you want to watch that. And under number conversions, you probably want to go here and look at all these conversions down here, including unsigned, signed short conversions for week 2. Adding, subtracting, NZVC, it's got all this stuff in here that you want to know about. So you could do that. And the nice thing is you're going to be working on this in the theory class as well. The beauty is you have practice quizzes. These practice quizzes for week 1 and 2 are going to be practice quizzes on course overview, which you don't care about for the lab, new MCO455 preface, which you don't care about for the lab, ASCII characters, probably number conversions. And the nice thing about these practice quizzes is you can do them 100,000 times if you want, and it will give you all the feedback in the world as to what you're getting right, what you're getting wrong, and you can do it again to get it 100%. But there's also some more practice quizzes that will help you out to get up to speed for your lab as well, such as this one here for adding, subtracting, NZVC, ANDing, ORing, exclusive ORing, all the stuff that's on Lab 1. And these practice quizzes, even though they can have theory sections in as well, will be then for your chapter quizzes, because if we take a look at your addendum, one of the things you're going to find is that the practice quizzes don't count for anything, but your chapter quizzes, especially this one here that you're going to get, is going to be 2% in the theory class. Okay, so there's going to be a number of multiple choice true-false questions in there. As far as your Lab 1 quiz, there's nothing handed in. It's going to be just a multiple choice question online and true-false, where it's going to say, is this the pattern of things that you got wrong on question 1A, or is this, or is this, or is this? And you pick the one that matches up with what you found wrong on question 1A. And then there's another question on 1B. Are these the pattern of things circled wrong on 1B, and so forth? And that's basically what your quiz is going to be like for next week. So as I said, what you have here in your theory section is a lot of the same stuff being covered in the video lectures that will help you out. Plus in the lab itself, when you take a look at the lab, find out about the ASCII chat. That is going to be a video. This is a YouTube video. This is a YouTube video. NZVC YouTube video. And if you want to just find out about the VBED itself, click here and you will find out about the VBED. This is one of the gimmies I gave you the other day. This one is definitely one of the things that you should see circled. So you're going to have to go through and say, okay, are all these conversions that are not bold, are they correct for octal and hex? And just basically circle those. Quiz is going to have the same question coming up exactly like this, and it might have a number of things circled, like maybe it's got this circled, that circled, and you say, no, that's not it. That's part A, and then maybe part B would be saying something like, well, I've got this circled and something else, is it B? So that's the thing you're going to do, and just select whatever pattern of things you got wrong that matched up with what's on the test. So that's basically where it's going there. It's not that difficult, but it does make you do some work. Here we've got 59, as we said, on page 26. you'll see that that's a capital letter Y, a 6F is a small letter O, small letter U, and a space, and so forth. And then on the other one, you're going to use it in the reverse thing where capital letter A is a 41. So it filled in a little bit just to give you an idea whether you're on the right track or not. So this is correct. You just circle anything on that same line that's wrong. This is correct. You circle anything that's not the exact conversion of that on those lines. So this is pretty basic stuff. And we're going to take a look at N, Z, V, and C. Now we've done this very briefly, but let's take a look at it again. I'm going to AE plus CD. E, if you want to do this, E, A, B, C, D, E, 10, 11, 12, 13, 14 in decimal. D, A, B, C, D, 10, 11, 12, 13. So we add these and we get 27. To convert this 16 into 27 goes 1, 16. We got a 1, 1. So our answer again is 1B, base 16. Now the B goes here and the 1 is carried to the next column. So it's not difficult to do these. So that becomes 1 plus 10 for A plus 12 for C, which is 23. 16 goes into 23. 1, 16, 7. So that's equivalent to 1, 7 base 16. The 7 goes here and the 1 goes there. Now let's take a look at a little program that you can do on the micro at some point. We can say A, which is a variable, a char variable, equals 0xAE, B equals 0xCD, and then C, which is another variable, is A plus B. Now one of the things you're going to find if you do this, this is the only thing that will fit into variable C because it cannot hold the extra bit called a carry. And that's what this thing is here. Okay, so the carry bit does not fit into there. So one of the things you're going to find is that we're losing part of our information. We've got 4 bits that everything is based on in terms, and we'll see this again shortly, N, Z, V, and C. So all things like, is this number bigger than this number? Is this number greater than this number? Is this less than or equal to, greater than or equal? All the stuff that you're doing in C all comes down to, at the hardware level, 4 bits. Now let's write this answer in binary. That's a 1, and then 0, 1, 1, 1, 1, 0, 1, 1. Now the most significant bit of this is our N bit. And a 0 means as a signed number, this is not negative. And this one here is our carry, so we write our carry down here. What you do is put 0, because this 0 says this number, 7B, is not 0. And the number 7B as a signed number is not negative. And I did get, yes, I got something called a carry, which we'll later see means that this is an unsigned overflow. The number does not work in the unsigned number system. As we validated, I think that the answer is definitely 7B. This is what our number is. Let's go here. So there's our number, and in binary again, it's 1. This is 0, 1, 1, 1, 1, 0, 1, 1, and 7B is indeed the correct answer. We're going to find that N should be 0, and it's not. So this is one of the errors that you're going to circle. And 7B is not 0, so that's correct. And it does have a carry. So the only thing in here so far that we've looked at that you have to circle is the N bit because it's not negative. 7B as a signed number is not negative, or in other words, it is positive. Let's look at 6A minus FE, and let's see if we can do it on this screen. 6A minus FE, so we have to borrow 1 from the 6, that's a 5, that's 1A, which is 26 minus 14. This number here is a C. We have to borrow 1 from the carry, that's 1, 5, which is 16 plus 5 is 21, minus 15, which is 6, I believe, so our answer should be 6, 6C. 6C. So we're going to circle this because this is not the right answer. Okay, so we're going to circle the 7B because that's incorrect. It's not a proper subtraction. But again, if you were to write this in binary as we did before, I think you'll see that the N bit is 0 because 7B, or 6C even, which is our right answer, is not negative as a signed number. And we'll see again why this is true. It's not 0. And we did indeed get a carry. So everything is right except for the actual value there. Hex, binary, octal are really 3 ways of looking at the same thing, where hex is the most compressed version of this. And you just regroup to get these numbers, right? And decimal to BCD, again, it's grouping in groups of 4, 1, 2, 4, 8. And the only real conversion that we're doing at all when you look at it, decimal and hex, which is the most compressed form of binary, that's the relationship that we want to take a look at and get an idea of what this really means. Now, one of the things that you'll see in question 5 there is it said 8-bit unsigned conversions. Now, 8-bit is a data type, in C is char. So when it says unsigned 8-bit numbers, it's really saying unsigned char. Char is our 8-bit data type. And if we want to put our hex values up here, this is say 00, which in decimal, it's really easy. 0 times 0 plus 0 is 0. And this is 7F, which is 7 times 16 plus 15 is 127. 80, which is 8 times 16, which is 128. And we've got up here FF here, which is 15 times 16 plus 15, which is 255. Now, of all of these numbers from 0 to 7F, all of these have the most significant bit 0. And the decimal numbers here are all positive. These ones here, because 7 is 0, 1, 1, 1, 1, 1, 1, 1. And 80, when you start there, that starts with a 1. So all these numbers from 80 to FF start with the most significant bit being 1. So these are all n equals 1. But again, the decimal numbers here are all happy positive numbers. So for unsigned char, all numbers are positive and n bit is ignored because it doesn't come into it. But that's different when we take a look at something called signed char. So there's our unsigned char. All numbers are considered positive and the n bit is ignored. But we've got another set of numbers called signed char, and you may have seen this back in Peer G2. You should have covered it. And they're different because this is minus 128. These again are hex. These are decimal. And this is minus 1. Now the numbers from 00 to 7F are exactly the same as before. This is 0 to 127. Now these numbers here, let's just put a line through here, these are called signed char. And this is what you can declare in your C program, either have numbers, 8-bit numbers as signed or unsigned char. Notice these have n equals 0, and in n equals 0, these are all happy positive numbers. But here, n equals 1 now means that these are negative numbers. So 8 zeros through FF, if you declare it to be signed char, are negative numbers in equivalent decimal. If it's signed char and it's 00 to 7F, those are positive numbers. So n equals 1 says, yes, I'm negative. N equals 0 says, no, I'm not negative, I'm positive. But for unsigned char, it doesn't matter whether n equals 0 or n equals 1, they're all happy positive numbers and the n bit is not looked at all. So let's take a look at doing some simple conversions here like we did before. And let's take a look at something like 52 in hex. Now 52 in hex, 5 times 16 is 80 plus 2, that's 82. Here, 52, that's again 82 because the conversions for n equals 0, whether it's signed or unsigned, are exactly the same. 16 goes into 82, 5 with 2 remainders, so that all works. But what happens if you have a number like A2? This is 162. But this A2 over here sure is not 162, is it? Okay, so the 80 through FF have a meaning for unsigned and a different meaning for signed. And what you're going to find is this meaning here for unsigned to this meaning here is offset by 2 to the 8 or 256 places. So if we know that, then if we take a look at A2, which is 162, we can say 162, and let's move it to the left 256 places, or if we want to do this by hand, is the same thing as saying 256 minus 162, and just remembering to put a negative sign here. So this becomes minus 94. So that's what this one is here. This A2 is minus 94. That A2 is positive 162. Okay. Now, how do we go back if we're given in a chart, say minus 94? Well, you go back the other way. You add 256, and then you divide 16 into 162 once, 16, bring down the 2, 16 goes into 2 0 times, and you've got A2, which is what you had before. So this is how you do signed char conversions. They're the same as unsigned, except when you have the most significant bit 1. Let's take a look at doing calculations with these. For instance, if I do FF plus 1, that ends up being 00 plus a carry. And what this means is this is an unsigned overflow. And we said, like, as we said before, A equals 0x FF, B equals 0x 01, and C equals A plus B. You're going to find that the C can only contain this, it cannot contain the carry. So part of our information is already going to be lost. But if you take a look at what this means in terms of our diagram here, that means I had all the money in the world, $255, I go get another dollar, and I end up with no money. And that's when C equals 1. This means that this is an unsigned overflow. It means that you cannot represent the value of that addition in the unsigned line. It goes over the bounds of the line. Also, we do something like a subtraction. Let's take a look at a subtraction such as 0.3 subtract 0.5. It ends up, I'll do it quickly for you. That's what it ends up being. And if you think about it, it means I go 3 units this way, and I go 5 units back this way, and I end up with FE. And so this is not correct. So anytime you add two numbers together and get an extra bit, such as two 8-bit numbers, which are char and get a 9th bit, or you add two shorts together, which are two 16-bit numbers and get a 17th bit, and so on. So if you add any two numbers together and get an extra bit or carry, that's an unsigned overflow. Now, if you subtract a larger number from a smaller number, typically that means you're going to get a negative, but you cannot represent a negative number on an unsigned line. So in both cases, this is an unsigned overflow, which means the result of the addition and subtraction you see here is not valid in the unsigned line. And let's take a look at a couple other quick calculations here. Let's do this one in red. Let's do 7F plus 1. If I say 7F plus 1, that's 80, and no carry. Look at that, which means I've gone 7F plus 1, 80. I'm still in my number system. Perfect. Well, let's take a look at that calculation as it's interpreted here for signed. I had all the money in the world, $127, got another dollar, now I'm $128 in the hole. This is called a V equals 1 or signed overflow. So some calculations will work in one number system but not the other. Some work in both and neither. Because 7F, as we saw, was a positive, and we added a positive and we got a negative. How can that happen? And it shouldn't happen, should it? If I add two positives, I should get a positive. When I don't, I've gone past positive infinity, and that is a signed overflow. Also, we take a look at this calculation, 80 plus FF. When you do that, that's 7F plus a carry. So the carry is telling us that this calculation will not work in the unsigned line, but let's see what it means here for the signed line as well. I was as far in debt as I could go. I went another dollar in debt. Now I have all the money in the universe. I think this is a guy that probably works for Donald Trump doing his income tax. But anyway, the bottom line, that is a negative plus a negative, and I got a positive. So if you add two negatives, you should get a negative. And when you don't, that is a signed overflow. If you add two numbers of the same sign and get an opposite sign, that is a signed overflow. It's gone past your number system's ability to actually represent that number properly. But what would happen if we took a positive plus a negative? Can we get a signed overflow? And the answer is no, because if you go positive, you go this way, and you go negative, you go that way, they cancel out. So this would be V equals 0. Also, if you add a positive plus a positive and get a positive, V is 0. If you add a negative plus a negative and get a negative, V is 0. So only this case here where you add two negatives and get a positive, or two positives and get a negative, do you have a signed overflow where V is equal to 1. So let's take a look at number B because it's the easiest one to look at. So this one here, most significant bit is a 1, which means this is a negative. And I'm adding a number that has most significant 1, which says I'm adding another negative. And what kind of result did I get? I got a negative. So V should be 0. Perfect. Nothing to circle here. Okay. So that's all fine and good, but then we got some subtractions. How do we apply this signed overflow or V bit here? And the concept is that what we do is we basically just change it into an addition. And let me show you how to do that. If we take a look at a decimal subtraction, 5 subtract 3, that can be written as 5 subtract positive 3, 5 plus negative 3. These are all the same, right? So if we want to take a subtraction such as this one and convert it to an addition, we just add the opposite value. Let's take a look at A here. So this number here is a positive, and we're subtracting this guy here, which is a negative. So if we were to change that into an addition, we rewrite that as a positive plus the opposite of a negative, which would be a positive plus a positive. So these two are the same. So this is a positive plus a positive. What kind of number did we get? We got a positive, so B is 0. Let's look at this guy over here. This one here is a negative. Subtract a positive, which should be the same thing as a negative plus a negative, isn't it? And a negative plus a negative, and our answer here is positive. So that one's okay. Let's see if we can work out the V bit for this first one, the first two. So AE, now if you remember, A starts with a 1. So that's adding a negative. And our answer here was 7B, which is positive. So V should be 1, and it is, so we're all good. Now we remember that this answer here is wrong. So this is 6C, right? So we're going to circle this anyway. But this is a positive, subtract a negative. So it's a positive, subtract a negative, same thing as a positive, plus the opposite negative, which is positive. And we got a positive, so V should be, V should be 0, shouldn't it? It says circle the following 8-bit sign conversions. Now, just to help you out a little bit with concepts at least, let's take a look here. If the binary has a 1, that means you should have a negative. So that's correct, at least as far as a negative and positive. This should be negative. This should be negative. This should be, circle. So if the most significant bit is a 1, it's negative, and the most significant bit is 0, it's a positive. So obviously that is one of the mistakes that we've got here. And again, the stuff that's in bold, the -49, the ED, the 1010, 0101, and the 124 are all correct. You have to make sure that there's no other errors in this chart. It says circle bit 6. Now the LSB, it says is 0. So this is bit 0. This is bit 7. So it would be this guy, bit 6. Now it says if this is an 8-bit sign number, is the number in question 7 positive or negative? Well, if you count and there's 8 bits there, the most significant bit 1, it should be negative. Now we've got a couple things here to finish off. And it says convert the decimal numbers. Now you can do this on a calculator easy enough, I guess. But let me just show you how you would do this otherwise. So 60,000. So you would divide 16 into 60,000. There we go. So what you do is you divide it in, and so 16 goes into that 3, which is 48, which is going to be 12. Bring down the 0, 16. So you're going to end up getting a number here as a quotient, and down here at the bottom, you're going to get a remainder for this first division. Now what you're expecting is a 4-digit number, right? Well, this remainder that's here will be this digit for the first division. Now if you divide 16 into this quotient, whatever remainder this will be this guy. And then whatever quotient you've got here left, 16 goes into that, the quotient that's left here will be here, and the remainder will be the other guy here. So it's not that difficult to do. It's just 3 divided by 16. You can verify this on a calculator. But what about something like minus 25,000? You don't add 256 because that would be for char, wouldn't it? Because this is a short, which is 2 to the 16. 2 to the 16 is equal to 65,536. So you'd first do 65,536. You subtract this, get 63504, and do the divide by here, and you should end up with the appropriate number. But then it says, is the 16-bit number 9A, which is 60,000, is it a signed or unsigned value? Well, let's take a look. The top diagram that you've got here is the unsigned short line, which is 16 bits, and the bottom one is a signed short line. And you can see the pattern 000 to 7FFF, 80000 to, it's very similar, but there's more digits. Notice 60,000 only appears in the unsigned line because it's not available in the signed line because it only goes up to 32767, and you got 60,000. So it's only available in the unsigned line because it doesn't exist as a signed number. Now, if I said some negative number, is it signed or unsigned? It'd have to be signed because no negative numbers exist in the unsigned line. If I said it's some number like 20,000, well, you'd say it's signed or unsigned because 20,000 exists in both number systems. What is the symbol in C for this and or an exclusive or? And not is not an exclamation mark. Okay, I'm telling you that. It's not. It's different. It's a little thing called tilde, or it's a little squiggly thing. So for this last question, what you have to do is, again, the stuff that you've got from before, let's look at it. Anything that's in bold is correct. This is correct. Now, what it's really asking, if this number here is not the same as the AB, then circle it. Well, it is AB, so we're not going to circle that because that's fine. That's correct. The 0F, is this number here the same as 0F? And it is, so we don't circle that. Now, as it's saying is, okay, if you take AB and end it with 0F, is it going to be 0B? If it is, don't circle it. If it's not, circle it. And is that then the same as this as your AND in binary? Then if we OR these two, AB plus 0F, is this a number? And is that the same in binary? So you're just going to circle the ones that are wrong. So this is lab 2, but notice this program that's here, this last one. If you can get this working, it's going to take 3, input a number, input another number, just like that chart. And then what's it going to output? It's going to output the AND or an exclusive OR of those numbers. Isn't that cool? So this would help you out quite a bit in doing that last question in chapter 1. And these are console applications, okay? And they require you to have things set up properly. So setting up an embed account, a serial driver. Now, to go over this just briefly so that if you want to work ahead a bit, the first thing you have to do when you get your Freedom K64 is you have to install the serial driver with the cable connected from your PC to your Freedom K64. It has to be connected. And then once you install the serial driver, you should go to Windows, go to Device here, and check to see what COM port has been assigned to the Freedom K64. Every time you take the cable out, but the COM port disappears. When you put it back in, the COM port reappears. So all that kind of stuff has to be done in sequence. So you're going to do the serial driver first, then you're going to set up PuTTY and do all this kind of stuff, and then you should be able to run console applications. Once you finish the Lab 1 quiz, which isn't going to take you too long, you should be working on creating all of this other stuff here.